Hello, I'm Manuel Bardiès and I'm going to present some example of use of software in clinical practice. So in this webinar, we're going to compare results obtained in the same settings but using different software. So this is my declaration of interest, and we're going to compare model-based dosimetry. So the first example here is obtained with Olinda version 2. So it's a model-based dosimetry, but as you can see here, the reference model is voxel-based. So a priori, it means it's a better definition of geometry, even though it's for a model rather than your patient. So the example that we're going to study is based on lutetium-177 dosimetry. So as you know, obviously, it's a medium beta emitter with a mean beta energy of 133 keV. And it's also a medium gamma emitter with low yield, but emissions of gamma of 113 and 208 keV. So in that specific example, and I don't claim it's a realistic example, we selected a residence time, so time integrated activity coefficient of 1 hour in liver, kidney, and spleen. So the point is to compare the results obtained, to analyze the results obtained. So Olinda is model-based dosimetry, so you input your residence time, and then it computes automatically because it's like an Excel spreadsheet, right? So for all the possible target, given the sources for which you input the activity or cumulated activity or residence time, for all the possible target, you've got a computation of the absorbed dose. I just manipulated slightly the results to display for every target. So you can see adrenal, brain, esophagus, eyes, and so on. You've got the absorbed dose in milligray per megabec. So the absorbed dose per administered activity. For the beta contribution, the gamma contribution, the total being the sum of beta plus gamma. And I added the percentage of beta and the percentage of gamma irradiation, and yes, indeed, the total should be 100. So what can we see? First of all, for all the source volumes, so the kidney, the spleen, and the liver here, you can see that these organs or volume of interest are those where the absorbed dose is the highest. So you have 2.81 minus 1, you have 10 to the minus 2, 10 to the minus 1. You can notice that for all the over target, you've got minus 3, minus 4, or even minus 5 or 6, okay? So first conclusion, the source organ or tissues always receive the highest irradiation, okay? Then the second conclusion is, as you can see, for all the source organs, the irradiation is coming massively from the beta component. 98%, 95% of the irradiation, 98% of the irradiation of the kidney and of the spleen comes from beta, 95% of the irradiation of liver comes from beta. And obviously the rest, 2-5% is coming from the gamma. Okay. And then, most of the irradiation and the high irradiation in all the source tissue and organ is coming from the beta component. Then the gamma contribution is negligible even for large organs like the liver. As you can see, the liver is larger than kidneys and spleen, but the contribution is still 5%. Then, speaking of target organs, you can see here that target-only organs or tissues are obviously irradiated mostly by gamma. And so the irradiation is low, much lower than for source organ or tissues. And it's, what you see here, 100%, 99%, and so on of gamma. With 3 exceptions. So let's have a look at these 3 exceptions. The first one is the adrenals. as you know, the adrenals are very, very close to the kidneys. So one can assume that some beta contribution from the kidney is irradiating the adrenals. Well, it cannot be the adrenals as self-absorbed dose or self-irradiation, because there is no lutetium in the adrenal in that example. The residence time and the activity was put only in kidney, liver, and spleen. So here the adrenal, the beta contribution, 23%, is in fact coming from the kidneys. Then for the gallbladder wall, same explanation, the irradiation is coming from the liver. And maybe more surprising, there is some irradiation of the lungs by the electrons coming from the dome of the liver. So yeah, that's why mostly, target only organs are irradiated by gamma, with exceptions. So now we go a little further and we realize that Olinda version 2 is considering a voxel-based model. So this is a section of that model. So you can see that thanks to the voxel definition of the geometry, it's quite it is quite a good representation of human anatomy, right? So the S value calculation is made at the voxel level. Beta and gamma contributions are considered. There is density correction, so it's quite a good calculation in a reference model that is realistic. Okay, but then if we compare with mathematical models, well, in mathematical models, you can see that the organs are clearly separated. So by for the record, mathematical models were the first that were observed in the literature, and they were the first used for S-value calculation and reference dosimetry. And the reason was that at the time, it was possible to define a mathematical model using equation, and that could weight something like hundreds of kilobytes, and that was enough with equations. You had a text file with equation, and that was defining your reference model, right? Whereas if you have a voxel-based model, so you have a data set that is much, much bigger, and that was out of reach in the 1975 or so, when the first S-value dataset were computed. So it was on mathematical models. But now we have voxel-based model. As you can see here, much more realistic. And because they are much more realistic, you can see that you have an interface between liver and lungs, liver and gallbladder, kidney and adrenals, and that explains why you can have some absorbed dose to the lungs delivered from the electrons that are emitted from the liver, and same for gallbladder and liver and adrenal and kidney. You would not have that if you were using a mathematical model, okay? And that is what we're going to see now. So here are the results obtained with Olinda version 2. I just mentioned that there's a computation of a total body absorbed dose, which is just the ponderated sum of all the absorbed doses. So I'm not 100% sure this is really relevant. It wouldn't be relevant in the context of therapy anyway. So it's just, it's a number, basically. Then comparing those results with Olinda version 1. So Olinda version 1 is based on mathematical models. So you can see to the right what they look like. So we take the same initial conditions, and these initial conditions are lutetium-177, same condition, and the same residence time. And these are, at first, the differences in the target organs that are considered in the two different models. So as I put the differences, so in red in Olinda version 2, you've got esophagus, eyes, salivary glands, and prostate that are not considered in Olinda version 1. In Olinda version 1, you've got breast, you've got muscles, you've got skin that are not considered in, and you've got uterus, because in Olinda version 1, it's an hermaphroditus model that has both, as you can see, testes, ovaries, and uterus. Whereas in Olinda version 2, you've got a male model, which is displayed here, and you've got a female model that obviously has no prostate but has ovaries and uterus. Then you've got the organs in red and green are those who are different in or not present in voxel in Olinda version 1 and Olinda version 2. There is also a difference on how the different tissues are considered. You see in Olinda version 1 you've got lower large intestine wall, upper large intestine wall, and you've got also, well, no, that's it. And that is transformed in Olinda version 2 in left colon, right colon, and rectum. So basically the gastrointestinal GI tract is not the same and not cut in the same way in Olinda version 1 and version 2. So we have to bear that in mind, because sometimes obviously the comparison itself is not possible because you don't have a corresponding absorb dose, because you don't have a corresponding target in the two models. Still, so now here are the calculation, here are the results obtained with Olinda version 1. So it's a mathematical model, but the same settings as were used for the voxel-based model in Olinda version 2. That is lutetium-177 and residence time of 1 hour in the liver, in the kidneys, and in the spleen. And as you can see here, you can see that the contribution of the absorbed dose in the source is 98% and 2% of beta and gamma respectively for kidney, 95 and 5 for the liver, and 98 and 2 for the spleen. So very close to what we got previously in Olinda version 2. However, for all the target organs, you can see that the irradiation is 0 from beta, everything from gamma. And that is due to the geometry. I mean, as you could see in the previous slide, in Olinda version 1, in the mathematical model, there is no overlap, there is no interface between the tissue and organs. So the adrenal and the kidneys are clearly separated, and so no beta emitted from the kidney can actually irradiate the adrenals. And that explains why it's not even calculated, so it's the absorbed dose is 0. So now let's compare the absorbed dose where we can. So for the source organs, so we have kidney, liver, and spleen. Olinda version 1, you've got the column of the results. Olinda version 2, you've got the column of results. And you can see that the ratio of version 1 versus version 2 is providing you with difference of a relative difference of 3%, 6, or even more, 18%. So it's quite a lot for the spleen, right? So let's try to understand a little more why we have those differences. We know that we have mathematical and voxel-based models, but then doing a mass correction, as explained in the previous lectures. So if you take the absorbed dose obtained in Olinda version 1 and then you do a mass ratio of the organs between Olinda version 1 and Olinda version 2, you have now a result, an adjusted result that is the same within 1% between Olinda version 1 and Olinda version 2, right? So that really says that in that context, the mass correction for self-absorbed dose is usually sufficient to get very good results in a way. So you can personalize your dosimetry by using model-based approaches as long as you do the mass correction. Okay, it's a first order, but it's a very good correction. However, if you compare the results of Olinda version 1 and Olinda version 2 for target absorbed doses, so the gamma component, you can see the differences that are very, very high. Sometimes more than 70% of relative difference between version 1 and version 2. And that is perfectly understandable because the volumes and the relative location of the organs, one in front of the other, vary a lot between the mathematical model and the voxel-based model. So obviously, the first reaction to that would be use voxel-based models because they are more realistic and they're more alike, the human geometry as compared to mathematical model. But it is not sufficient because, in fact, it's very difficult. I mean, we have no easy way to correct for between model and patient-specific dosimetry. We cannot, for cross-absorbed doses, there is no correction that is easy to implement. So that's the issue. Cross-absorbed doses cannot be corrected, okay? So here are the conclusions. We have different models in the literature, and we have recent models, we have old models, we have results that have been published in the past for different radiopharmaceutical using mathematical model. Is that a big deal? Not necessarily. For self-absorbed dose, as was seen, you can do mass correction, just a mass scaling, and that is a correction that actually works well. But for self-absorbed dose, for non-penetrating radiation, like mostly lutetium-177. The conclusion may not be the same for iodine-131, for example, where 2/3 of the energy is emitted by gamma, right? So these conclusions are only valid for one geometry and one radionuclide. The gamma contribution is most often negligible, especially in the context of therapy, and it's cool because it cannot be easily adjusted. Then difference between voxel-based and mathematical model-based dosimetry. The impact is mostly for cross-absorbed dose. So really the clinical relevance depends on what is the objective. So when everything is said, it's the clinical situation that indicates which model you should select or which model you should use for clinical dosimetry or for selecting such or such algorithm. And with that, I thank you for your